invite him to simplify chemical engineering for us. Sir, please.
Dr. Chopra, who has made it possible for me to come here and talk to all of you. I thank Professor Santosh Gupta and Professor Srihari, who made all the excellent arrangements to make this visit possible and very enjoyable. I am a teacher, therefore talking to young students is always a great pleasure, because we get positive energy from you, and it is you people who provide me with the motivation to work and work hard. Now, Professor Srihari has been very kind and gracious in his words of introduction. I must say he has erred on the more generous side more than required, but though I am at the receiving end, I am not going to complain on this occasion. In the tradition of modern TV, let me begin with a commercial. I come from the Indian Institute of Science, Bangalore. We have a beautiful green campus. It's more like a botanical garden. The students think we are like a zoo where the species, genus, faculty are roaming around. Our department started as a wing in 1943 in Pure and Applied Chemistry department. We became independent in 1947 and renamed Chemical Engineering department. We present a very modern phase of chemical engineering, starting from biotechnology, pharmacochemical engineering, nanotechnology, energy engineering, molecular simulations, biomolecular engineering, flow of complex fluids, and CFD. We are a very small department having only 11 faculty members, but we have overlapping interests and excellent facilities for doing very good, high quality experimental work. We have only MTech and PhD programs. We do not have BE programs. So, the postgraduate students form the center of our attention. So, I think we have a unique place for carrying out postgraduate studies, and I hope some of the young students here will choose to study in our department, and we will be happy to see you there. One is very excited. They accept immediately, yes, yes, I will give a talk. Then the time for giving abstract, title, all this starts. Then one becomes a doubting Thomas. So, what to talk about, what is good, what is attractive, what is at a level where I can be heard and appreciated. So, I went through all this. Then suddenly I remembered my age. I have started chemical engineering more than 55 years ago. But I tell you one thing, even at my old age, I am not completely outdated. Outdated, but not fully outdated. Quite a lot of things. So, I thought I will share that humble experience with you, but I promise to present more powerful examples towards the end of my talk to illustrate the very same idea which I am talking to you about. It is a very old topic. All of you have seen it. Crystallization is a very famous unit operation, and here is how you can grow sugar crystals in your home. Evaporation, and if you are forgetful like me, this evaporator will turn into a chemical reactor, produce a whole lot of carbon and smoke too. Reverse of absorption, that is desorption process. I am sure you have done this sometime or the other. condensation, thus the formation of droplet phase from vapor is a beautiful example of this onset of monsoon in Kerala. Then growth of solid phase on pipe walls, what we call as fouling of heat exchangers, but here is a more spectacular example with which a lot of people in this hall might be familiar. This is growth of asphaltene phase on oil pipelines, which chokes the oil pipelines itself. Okay. So, what we should want to learn about this phase formation. So, one thing is you should like to know when a phase will form, then how fast it will grow, and if one of them is dispersed phase, then what will be the size of the particles of the dispersed phase. That is what we should learn. So, I will begin with a science which tells us when nothing happens. Very important for you to know this. That is thermodynamics. Okay. So, I got this hot water, hot coffee, mostly water. I put a thermos flask as an equilibrium. Therefore, the chemical potential of water in liquid and vapor, they are equal. That is what thermodynamics tells us is an equilibrium. Another example is a soda bottle which you have not opened. There are two components. There is carbon dioxide, chemical potential of carbon dioxide in both the phases is equal. Similarly, chemical potential of water in both the phases is equal, but this example is different because the chemical potential of water is negligible compared to chemical potential of carbon dioxide is 10 times more. Okay. Now, since chemical potentials are equal, there is not even a potential for change. No change is possible. There is no potential for change. Nothing happens. You can have many phases. All the phases will be in equilibrium. No new phase will be formed. So, we know when a new phase will not form. So, how do you make things happen? How does it change? You can only change by creating a driving force. Without driving force, there is no change. We have to create a driving force. This is very, very common in chemical engineering. What you do is, you bring two phases where chemical potential is not equal into contact. Every unit operation is this. You can think about it. Okay. So, here I pour this water from a thermos flask into a cup. I exposed hot water to cool air, and the amount of it will decrease. The amount of the phase with less chemical potential will increase. So, water will go from liquid phase to vapor phase, and you see this water vapor rising from the interface. But here the driving force was not large, it is small. You can do the same thing. You can open the soda bottle. Now, you expose water containing carbon dioxide to air, which hardly contains any carbon dioxide. Therefore, carbon dioxide must go from liquid phase to vapor phase. But there is something different here. There are bubbles which are formed. Bubbles present a huge surface area. Therefore, now the rate of mass transfer is very, very large. Therefore, the decrease in the free energy of the system is more rapid, is changing very, very quickly down. Okay. So, we created driving force. We find in one case very slow change is there. In one case, change is very rapid because a new phase has been created. So, we ask, when free energy change can be so rapid when a new phase is created, why is it not created when the driving force is small? Because everybody tries to do things fast, including all irreversible processes. They try to maximize the rate of transport. Okay. So, the next question is, we understood when a new phase can form. The question is, why is it this phase is forming only in some conditions? So, for that we examine the interface that is separating the liquid and the vapor phase. You will see the molecules at the interface on one side see low density material, on the other side they see more dense material. Therefore, molecules from the more density phase are attracting the molecules very rapidly, whereas those on the other side are not attracting this so much. Therefore, molecules at the interface are seeing less attractive force, therefore, they are more energetic. They like to fly off. But unfortunately for them, the surface is under tension. The tension keeps the molecules down. You see that here. Here is a water strider walking on water, and you see these dimples. These dimples are putting, they are exerting a tension to make the thing float up. So, if you want to walk on water, somehow try to practice this trick of creating a very steep curvature on the interface, then you can walk on the water. Okay. So, if you want to now create a new phase, you must create a new interface. That means you must create more energy, otherwise you can't do it. So, the driving force must be such that so large that you can create a interface. You require more energy. That is why when the driving force is large, you are not able to create a new phase. Okay. This is called more is different. This is a slogan of complex theory, theory of complex fluids. More of the same is not the same. More of the same is qualitatively different. So, when the driving force is large, you created a new phase, not the same old thing, something very, very different, and phase formation is an example of this. Okay. When does actually it happen? Okay. So, I told you energy driving force must be more. So, we try to estimate this. So, I got molecules. If I want to create a nucleus of size r, 4 pi r squared is its area. Okay. I multiply that by some number density on the surface, different from the bulk density, it is on the surface only. So, that is the number of molecules. I multiply that by the surface energy, therefore, I got the surface energy increase when I create a surface area. But I create a driving force. So, when a molecule is transferred from one phase to the new phase, all the available driving force has decreased. So, the decrease in the free energy is the number of molecules in the sphere, the nucleus I created, multiplied by the driving force I provided. Chemical potential must be negative, otherwise there is no change. So, the volumetric change is decreasing, surface energy is increasing. The sum of it is a total free energy change. Okay. In the beginning, when r is very small, then surface energy term dominates, and you see surface energy is increasing, total free energy is increasing. But when size increases, then the volumetric term dominates and negative takes over. Therefore, the sum goes through a maximum and then decreases. So, if somehow you can manage to create a nucleus of that size, then it can grow because free energy will decrease. So, the energy that I must have must be sufficient to create this critical nucleus size, then I can grow. Question is, how can I create so many molecules? Critical nucleus size is not very small. It could be 10 molecules wide. It could be a nanometer. So, how can 10 molecules get together? They are always flying around here and there. So, how do they actually get together? So, there is one model where by fluctuations, like crowd, you see crowd moving around, some are bumping into each other. So, some clusters are formed, and if that cluster that is formed here is of the critical nucleus size, it will grow. If it is less than that, it will dissolve. That is called Lamer mechanism. It depends upon the fluctuations. Those fluctuations are always there. Okay. There is another mechanism that is called organizer mechanism. I can give you a very simple example. Suppose Tendulkar applied outside the door. All of you will run away leaving me here, He is a nucleating agent. Okay. He is able to gather people and he can nucleate. This is called a template mechanism, is very widely used. You create templates by loose attractive forces, it will gather enough number of molecules and make a nucleus. It turns out this mechanism is very widely operative in forming metal clusters, about which I will talk to you a little later. Okay. Now, things can happen. I told you when things will happen, when a nucleus size can be created. But there is something very, very important about which all the industry people talk about. It's called bottom line. Bottom line is a profit you make. If you got a very big factory producing at a very, very low rate, no bottom line is negative bottom line, not acceptable to us. That is why chemical engineers are always worried about rate of chemical reaction, rate of mass transfer. Rate is the central thing, because you like to produce things at a rapid rate. Only then you can make profit. So, for everything we should learn what is the rate at which things will happen. So, there is this nucleation rate. Okay. If you think surface energy is a barrier and chemical potential is the driving force you are giving, then you can formulate an expression like Arrhenius expression. Activation energy barrier overcome by thermal energy, that is why you get delta E by RT. Now, here units are different. This combination you can figure out by using Buckingham pi theorem. I leave it to you people. One has area units, another has got volumetric units. You can easily figure out this. Okay, I'll give you how you can apply this law. Suppose I got a solution, then chemical potential difference is proportional to log of concentration if you got an ideal solution. Therefore, chemical potential difference is log of C by solubility, which is the equilibrium value. That is called supersaturation. A solution can form a crystal only when the solution is supersaturated. That is why you create supersaturation. If you got a vapor phase, is the vapor pressure divided by saturation vapor pressure is indirectly the superheat that you got. When you raise the temperature, then you are raising the vapor pressure, therefore, you created superheat. The other rate is rate of mass transfer that everybody knows here. We use film theory. Film theory will tell you how to calculate the mass transfer rate, because that is the mechanism by which particles will grow. So, if I got solutions, I use concentration difference. If I got gases, I use a partial pressure difference. This is very straightforward. Now, this is one of the most central themes of chemical engineering. What are chemical engineers famous for? For making balances. They balance mass, energy, of course money, and maybe girlfriends, maybe boyfriends, whatever. You can balance anything you want. Okay. So, we have got this holy law. Rate of input plus rate of generation is equal to rate of output plus rate of accumulation. For everything, if you know this, you know all of chemical engineering. All of transport phenomena is only this. There is nothing else, only this. Okay. So, suppose I want to batch crystallization. Okay, what should I like to know? I started this batch crystallizer. How many particles I am able to form at a given time, at a given batch time? What is their size? What's the rate at which they are growing? That is what I like to find out. It's a batch reactor, input and output are 0. Therefore, rate of accumulation is equal to rate of generation. I'll make a simple assumption which I'll relax a little later. Let's say particles are not agglomerating, they're not breaking. Therefore, the only way particles can be generated if they are nucleating. Therefore, rate of accumulation is equal to rate of accumulation of particles is equal to rate of nucleation. Very simple. Okay. Now, I want to calculate mass balance of the solute, because I gave a solute, that is why crystals are growing. So, the rate at which the volume times concentration, that is the amount of solute in a solution is changing, because when nuclei are formed, they have taken off mass from the solution. Crystals are also growing by absorbing solute from the solution by mass transfer. So, number of particles times area is the area per unit volume multiplied by volume gives you area mass transfer coefficient driving force. That is all, very simple. Sometimes you may generate supersaturation, and it is also important. So, that is this factor G, which I will use a little later on. Okay. So, all you have to do is solve those two equations, very simple, nothing else to be found out. I make a mass balance. I start out with initial concentration C naught. At this time, V into C naught minus C is the amount of solute I have used, number of particles is NP, divide amount of solute by number of particles, you got average size. Very easy. Nothing at all very, very complex. All I have to know is how to solve these equations. There is a very famous physicist called Dirac. Okay. Dirac said He is the one who invented the quantum theory of electrons. He said, you understand an equation when you can predict the results without solving the equation. Okay, you should not solve the equation, you should know what the equation is telling you before you solve the equation. So, every time you write an equation, please think about it. What is it telling us? Okay, so I want to do that here. So, as constant, therefore, this negative term is growing, therefore, nucleation rate will fall down. Okay. So, as the process is proceeding, nucleation rate is coming down. But C can only decrease by mass transfer, there is no other way. Okay. But unless area is there, there is no mass transfer, but area is not there, particles are not there. Say a little loop. So, what does it mean? Till particles are created, nucleation will dominate, because there are no particles, mass transfer is not there. When particles have become very large, mass transfer will dominate, nucleation will die. So, there is a little window where nucleation rate dominates, afterwards growth dominates. The window of the nucleation period is what my focus is. So, here is these equations, and what I should like to know is, having learned that this nucleation period is dominating, how can I use this to